Hello, everybody. I'm Thomas. And yeah, before starting, I would like to say a couple of things. First of all, many props to the guys that are organizing this. I'm very excited to be here and really excited to see an international conference being held in my hometown here in Thessaloniki. Definitely feels really, really nice. And so I'm really happy to be here. Having said that, I've been talking to people around in the companies outside yesterday and a bit today. And to be honest, I find it a bit disappointing that things like category theory, functional programming are not that popular here, not that hot. I don't know, as I mentioned, I live in London. I'm part of the developer community there. And functional programming and category theory is booming. It's everybody tries to learn Haskell, Scala, Idris, I don't know, studying category theory. There are functional specific only conferences. There are consultancies in Poland about functional programming, big conferences in Spain. And this I would be really keen to see also happening here. I truly believe it's a very hot topic. It's considered amongst, I don't know, blockchain and deep learning, functional programming is there. And I find it very weird that this is my feeling, maybe I'm wrong, but my feeling is that this is not such an interesting or hot topic here. Hopefully, after this talk, you might get some more interest. I don't know, this will be my target. So category theory is not only for mathematicians, but spoiler, it is also for software developers. So who am I? As I mentioned, my name is Thomas Kaliakos. I work for a company called Ovo Energy. It is a Scala shop and a functional shop, most of the code base in Scala and pure functional way. And that is my Twitter handle and my GitHub username. So what is going to be the agenda today? We're going to talk about history and why category theory is relevant. An interlude about why types are cool. About pure functions, what's category, a monoid, a functor, and some conclusions in the end. Disclaimer, there's going to be a lot of arrows and quite some Scala code. And another disclaimer, apparently I'm no expert in category theory. This is going to be the quite pragmatic perspective from a software developer who has studied category theory. And the goal of this talk is to give you a feeling rather than maybe a deep understanding of how it feels if you study this kind of stuff. So let's start. History. Why category theory is relevant? Programming is about structure and logic. More specifically, it's about composition and abstraction, or even better, compositionality. This is a very simple term, but very, very difficult. Because what do we mean by compositionality? Because we mean that the behavior of the whole is the sum of the behavior of the parts. And it's something that easier said, it is very easy to say, but difficult to do. It's very, for example, in this jigsaw puzzle, every single piece, in order to put it, it's only affected by its neighboring pieces. This does not happen always with our code. We might write a function that does something on the screen or affects a global variable somewhere else. So compositionality is a very important thing of programming, but it's not a very easy thing to do. And then abstraction. Here you can see a map of the underground in London. I was keen to use a map of Thessaloniki's underground, but I couldn't find one. So I used this one. And as you can see, abstraction is about subtracting information, throwing away information. We want to focus on certain things that make sense to us. This map, for example, is not very accurate, geographically speaking. The stations, the way they are aligned, they're not, their location on the map does not correspond in their location in real life. But this is an abstraction so that we get a sense of where is the next stop, where we should change lines, and this kind of stuff. So programming is all about these two things. And about history, in the 40s, we had an assembly language, which was a very, very low-level language. Then in the 60s, 70s, we had structured programming, we dropped the use of GoTo, and in the 80s and 90s, we had the object-oriented, and it feels like every time we went one level of abstraction higher. We had some no structure at all, we could say assembly language, very close to the machine. Then we created some structure, some functions. Then we started creating objects. And today, as it's mentioned in Wikipedia, there is increasing support for functional programming in mainstream languages used commercially. I don't know, probably most of you people, if you're developers, you would be familiar with this book. It's the famous Gang of Four design patterns. And up until recently, it was the consider the Bible. Like the way to structure code, you would go to this book, find like which specific design pattern you should use, and apply to your code. But what strikes me is like that all these patterns were more like empirical, were like there was no solid theory behind it. There was no solid like foundation behind it. There were like some principles, like the solid principles. But aside from that, this was rather empirical and like practical outcomes of people that wrote very like thousands lines of code and like concluded that, yeah, this is the way that you should structure our code. And yeah, probably if you remember this, you're not that young like me. This is like the strategy pattern in UML. And this is like a quote, actually 2 quotes from Donald Knuth, that science is the knowledge that we understand so well that we can teach a computer. And essentially that if you understand something that good, you can teach a computer, maybe it's not science, but it's art. And this is like from a guy that wrote The Art of Computer Programming. Like he considers, as in the second quote is mentioned, programming is the art of telling another human being what one wants the computer to do. That maybe signifies that still we don't have a good grasp or a good understanding of how to structure code or like how to program. But why not use the most well-known language to communicate ideas? Like a language that has been used around for quite some time, like for 1,000 years, I would argue. And that language would be maths. But even maths, there are like quite many ways to structure logic, like there is formal logic, saying that, for example, all mammals are animals, it's true, and all cats are mammals, this is also true. Then you can induct that like all cats are animals, this is also true, like this is formal logic. Type theory, where we have types, and category theory, which we're going to talk in a bit. So these are like different branches of mathematics. So which one should we use for coding, like in programming? Or maybe they're not that different. The famous Curry-Howard-Lambek correspondence proved that natural deduction, which is like logic, simply type lambda calculus, which is like type theory, and category theory have a one-to-one correspondence. This is like something that when I found out blew my mind, that like 3 different branches of mathematics actually have a one-to-one correspondence. Like if you express something in one thing, in type theory, you can find the equivalent in category theory, or like in logic. So stuff like this turn mathematicians to become philosophical and start saying, okay, maths, maybe actually they're not invented, they're discovered. It's like an innate truth of the universe that we're discovering, but like doing our research and everything. Some people, though, argue that maybe it's just a projection of like our human mind, the human mind works. I don't know, I will leave the conclusions to you. And this is like a way to depict this correspondence. The important thing, like in the top row, we have like types, and the bottom row is logic. Like the first arrow, like it's function on the bottom, on the top left, excuse me. It's like a function. Function, what is it? If you give me an A, I have a function, I'll give you a B. This is the same thing as induction in logic, which says, if I have an A, I'll give you a B. Or Cartesian product, which is the X. If you have like 2 things, like a tuple, let's say, it's the same thing as saying a logical AND. And the same thing like for tagged unions, that's the same as a disjunction, and like the unit type that corresponds into falsehood in logic. Yeah, it's not that important understanding this, and it's actually math that I don't have a very deep grasp of it, but the important thing is that you can translate one to another. This is like the important thing. And all this mapped to category theory also. This was actually the 3rd part of the correspondence, like Lambek found out about the correspondence a bit later than Curry-Howard. This is why initially it was only Curry-Howard correspondence. An interlude, and hope to convince you that types are cool. Why is that? We have the same function that just parses an int. Like you have a string, and it returns an int. In the first case, in the left case, it's explicitly mentioned in the type that this might return an int in a try. Like this is something that might succeed or might fail. You're not sure. Whereas in the second case, the thing blows up, throws an exception. So in the caller code, you have actually to wrap it in a try-catch statement. I would argue that in the first case, it's much, much better. The caller knows explicitly that this thing might fail. It's not like hidden or anything. And you could argue, okay, well, in Java, we have also checked exceptions, which I would argue it's not that good. Because checked exceptions cannot work like with higher order functions, like with functions that take as parameter other functions, aside from the fact they add a lot of boilerplate. Or safe head, this is another example of like why types are good. Safe head takes, if you have a list, you return like the head of the list. But in the case that the list is empty, what do? In one case, you can return a null. So the caller got a null. OK, what was the case? We don't really know. But the option is explicitly in the type. You might get a value back, but you might not. The option is the Scala equivalent of optional in Java, to have some, like, for people that are not that familiar with Scala notation. And lastly, but maybe most importantly, if we have a function that's called is it weekend yet? In one case, we take a string as a parameter and we return a Boolean that signifies if it's like the day our input is Sunday or Saturday. OK, is it weekend? In one case, we just take a string. In the other case, we explicitly create a type for the different from the different days of the week. OK, this is, you could say that this is something like enum, but it's not exactly the same. Anyway, but this is the notion that you narrow down your input. I would argue that the right part of the code is much better. What do you think? No. Or what is your intuition? Maybe they're the same. Maybe having a string is OK. Right. Yes?
You have a type there, so it's better.
Sorry, what?
You have a type there, so it's better.
Why? What do you mean it's better?
Making a type, for example.
A typo. Yes, that exactly. That is towards the correct approach, which means that like the possibilities, the different combinations you have on the first case is 2 to the power of infinity. Why? Because the different inputs that you can have are infinite. You can provide infinite strings. Whereas in the second case, it's 2 to the power of 7. By the way, this is not like accidental. In category theory, the functions are like called exponentials. This is like, no, but yeah, we don't have time to talk about them today. So in the second case, you have like explicitly 128 different cases. If you're crazy enough, you can write different test cases for all your different cases and be definite that your code is like not going to break at any time. Having it visually, it can be depicted maybe like this. Like if you have loose types, you have to put tests so that you can validate that your logic, the flow, the information flow in your program is the one that is expected. Whereas if you have very restrictive types, you narrow down that space so that you can have more confidence that like your flow and your logic is correct. And this is actually the source of the argument from some people that heavily use type systems and strongly typed systems that like if it compiles, it works. This is, yeah, a bit debatable argument, but yeah, this is like the source and the mentality behind it. How is everything combined? Functional programming is about writing programs using pure functions. Category theory gives us a way to structure or compose pure functions, gives us abstractions. Category theory gives us abstractions that we can use. And programming languages with expressive type system make it easy to materialize those abstractions. What do we mean expressive type system? Type system that is strongly typed, statically typed, and has higher candy types. Like it has a list that takes an integer and creates like the type list of ints. Takes a type parameter. This is like higher candy type. So this is how everything is combined. But I mentioned in 2 cases pure functions. Do you have an idea? Like, have you heard about pure functions or purity? What do you think it is? Yes, please. I make it a bit interactive. I don't know. I think it's more. It's better that way.
For every iniquity, you get the same output.
That's a fair approach. That's a fair definition. But surprisingly, the definition is much more strict, and it's this one. It's about referential transparency. This is like the term. If you replace an expression with its bound value, the result does not change. What does that mean? It's a bit confusing. Let's see an example. We have this example. On the left-hand side, you can see like we have S, which is like the string low. We convert it to uppercase, and when we call it 2 times, we have like S twice, and it's S plus S. In the second case, we replace that bound value with the exact statement. Okay, so we say load dot to uppercase, concatenated with a load dot to uppercase. And the result is exactly the same. Like if you print S twice, you'll get low, low, both cases. So purity. What happens in this case, though? You have an iterator, like you iterate through a list. And you get, you store that value in a val, next, and then you add those to the next 2 times. And if you replace next where it is called, in one case you'll get a 2 because it's 1 plus 1. In the other case, the iterator moves, so you get 1 plus 2 equals 3. Different results. They break referential transparency, not pure. This is like the very strict definition. And out of this, you might get intuition. It's like this thing that you mentioned, like you get for the same input, you're definitely like you're getting the same output, or you don't create side effects. And we're going to talk about this in a bit. But what happens with I/O? This is actually a very common cause of confusion about functional programming. What happens in I/O, right? Example in this case, we want to read a line from standard input. We want to read something. Okay, how can this be pure? For example, if the standard input contains, like if we type Voxxed and then days. In one case, we read just once. Okay, we have this read line, and then we concatenate these 2 strings, but we essentially read only once. So it's like Voxxed, Voxxed, concatenated. In the second case, if we replace that call though, we read 2 times. So the end result is different. In one case, we have Voxxed days, in another case, we have Voxxed, Voxxed. We have a problem there. So maybe I/O is not, we're not able to do like in a pure functional way I/O. So what our programs can do? So maybe it's like for programs that are very small or something. But what's the point, right? Well, the truth is that we can have I/O in a pure functional way. And the way you can do that is like the following. In the specific example, we use like library called cats from category. It's a very famous library in Scala. Cats affect I/O. Which actually I/O is like a monad, which we won't talk about monads today, but anyway, yeah, it's an abstraction. And what it does, a very simple thing. It's a description that an I/O operation will occur, but it is not actually being executed. So it is a big shift in mentality and a big shift in the way you write code. The way you write code is not about executing things. It's about a descriptive way. You describe what your program will do. And in the end of the world meaning at the end, after you have combined everything and you have structured your code, you call this res.unsafe run unsync. And this is the very interesting thing that like referential transparency, or like, as you said, like your state, the way to break referential transparency is when like a caller notices that a function that has called changed something that in the view of the world, like changed its state, right? But if that happens after there's no code to inspect that, you don't break referential transparency. So what you do is essentially you combine all your I/O operations, you combine them, so in the end you get one I/O, and you just execute that. So everything is pure, win. So to recap, a side effect is something that breaks referential transparency. Pure functions do not have side effects. I/O can be done in a purely functional way, and pure FP means local reasoning, which means compositionality. This is like the true essence and like the true big benefit of writing purely functional code. Local reasoning. You don't need to have in your head anything else other than the parameters that you pass inside your function. Nothing else. Like our Homo sapiens brains, I don't know, we have a working memory that can keep a hold of 7 things or something. Imagine having a function that mutates a state there, like prints in the screen, writes a file, so our mind blows up. And this is the beauty of functional programming, that essentially when you argue about things locally, you don't have this. Everything is composable in a really nice way. But you have to do these kind of things, having to, as we will see, using types to model category theory abstractions. So what is a category? Imagine using this model to depict our programs. What is this? Like having a graph, a directed graph. What is this graph? Every node is a type, and every arrow is a function. So we have ints that map to strings. If you get a toString method, like you go from ints to strings. And you can see that there is also option that like creates a new type, like goes to option of string. Option of string is a different type from string. And then like the equality to 2 creates a Boolean. And those two functions can compose with like compose is a higher order function, takes functions as parameters. And those two functions compose. What is this exactly? Well, this is a category. From a mathematical perspective, a category is a bunch of arrows and objects. For example, this category C, but it has to have something specific properties. My mic stopped? Okay. Identity and composition. Identity is the yellow arrows and composition are the red ones. What does that mean? It means that every 2 arrows, if like they have the common start and end, they must commute. For example, here, if you go from A to B and B to C, you must have an arrow that goes from A to C. It's the same as functions, right? If you have a function that goes from int to string and from string to bool, you must have a function that goes, if you compose them, it goes from int to bool straight away. And must have identity, which seems weird, but this is like the point of category theory. It's like we're talking about objects, and what an object can be is very abstract. Like you don't know. It is not. You could argue like functions are like mappings between sets. Okay, you have a set of ints. Like you map every single int to another string. But like in category theory, you talk about objects. It's so abstract. You're like you go that high level in abstraction that essentially you cannot see what is inside an object. And the only way that you can argue about stuff and talk about stuff is if you have arrows between them. So the identity arrow can be used if it is like we have 2 arrows that go from A to B and back B to A, sorry. If you want to say that there is an isomorphism between these 2 arrows, like they do, the second arrow does the reverse of the first one, you must say that their composition is equal to the identity. This is like, in these kind of situations, you use like these structures. And there are more, there are the laws, as they say. So the identity must be symmetric. So like if you compose an identity with a function from the left and the right, it shouldn't make any difference. And the composition must be associative. What does that associative means? That like if you compose 3 functions, it wouldn't make any difference. Like it doesn't matter where you put a parenthesis, if you put a parenthesis. So it's like, it's the same thing. If you didn't have a composition, then 3 different functions will create 2 different compositions. And it would be difficult to argue about this. So to get back, this is how it looks. This is actually the category for us developers. This is like the category we're operating in. The functions are like the arrows, and the objects are the types. And the functions compose as the arrows compose, and we have also this identity that's like the trivial function that takes a parameter and just returns it. This is called the category of types and functions. Let's start talking about some abstractions. What's a monoid? We see first example, we have string concatenation, like string 1 concatenated with string 2, string 3, and we have the empty string. The second case, we have integer addition, and we have like the number 0. Or multiplication, have number 1. Or list concatenation, and have like the empty list. Is there a pattern there? What's like common there? Can you see anything? Or they're just arbitrary operations and like some elements of the operations? Well, the truth is there is a pattern. What kind of pattern? There is a set. In every case, there was like the set of integers, the set of lists, an associative binary operator, as we said, e.g. addition, or like multiplication we said, and the unit, or the identity. In the example of addition, that was 0. In the example of multiplication, that was 1. And actually, yeah, this is set theory, though. And now we see like how stuff get combined. Like we go from set theory to category theory. This can be modeled in category theory like this. It's a category with only one element. So you will say, though, yeah, but we had elements, like we had all these different things. How like this relate to a category that has nothing? Well, you can map in the functions the elements of the set. So you can say that like the different arrows are essentially operations that act like on the members of the set that you had in set theory. And also everything here composes. For example, if you have +4 and +2, you know you will have for sure the +6 arrow there. So this is an abstraction, okay? How can you use that in code? This is, if you translate this abstraction into code, it's a trait, it's the same as interface in Java, that you have a value that's like the unit value, like the one that if you use it in a composition doesn't make any difference, and the composition itself that takes 2 elements of the set and returns one of those. And the specific example for int. And you've definitely seen them. This is like how you fold over a list and sum their elements. And I think it's the same in Java. You have like reduce there. So reduce and fold take a monoid as a parameter. And so if we had that in mind, we could rewrite that code like that. So use the monoid and say explicitly that if it is if the list is empty, return the identity of, or if it is not, compose the two things and recursively operate the same function in the whole list. And how can we use this in our code? For example, we have this case class that's like a crate, has a weight that's just an integer and a boolean that if it is true or not, if it can be stacked, this crate. So let's say we have a list or an infinite stream of these crates, and we want to combine them. What do? You create a monoid. And what would that monoid look? Where the identity element would be a crate that has 0 weight, and the can be stacked would be true. And the way you compose this is by creating a new crate that has like the sum of the crates of the two previous ones, and you do the AND operation in the two things. And this is actually not surprising at all. Why? Because from category theory, we know that this is called a product. Okay, we have two monoids there that they get composed. The first monoid is like the addition along with element 0. And the second monoid is like that operates in booleans, that you have the logical operator AND. And you have as the identity element true. So by combining two different monoids, you get a new monoid that you know like for sure that you can create. Functors. This is something that we actually do very often and we don't realize. We add context in a specific type. So you can see we have like Boolean integers. It's all about types, right? We create Boolean integer strings, and we want to add some context, some metadata, some more information about that. What kind of information? Well, this specific type might be there, might not be. It's an option or optional in Java. Something that might be there, but some point in the future, we don't know yet. Or something that might have exploded and we still don't know. So you create these different types using these type constructors like option, future, and try. And you have these functions, like string length is even to string. These functions operate, you know that they operate in regular types, right? The first one, like you get from a string an int, the length of it, you get a Boolean out of an int, so they operate in regular types. Can you reuse them in like the context of these wrapped types? Yes, you can. How? Using functors and using this single function of map. Map takes a function from A to B and wraps it and uses it in a context of FA, F to B. Or this is how it looks from a categorical perspective. Having a category, as we were talking about, having a category that's like with identities and morphisms and everything, you lift it, as we say, to a functor. So we have another category that's like F to A, F to F. You go like from the world of ints, you go to the world of list of ints. And you know that all your operations that were operating in ints will operate also in the world of lists. And the same goes for option, the same goes for future, for tries, for everything. And actually, the definitions like a functor is a mapping between categories that preserves structure. And what do we mean by structure? We mean that there is a mapping for everything. There is mapping for objects, there is a mapping of identities, there is mapping of functions, and that the composition is preserved. And this is what is mentioned here. For example, as we said, we talked about list. This is the example of a list. Like we get to string function that goes from an int to string. We have the identities, and the list functor raises it to the world of list of ints. So some conclusions. With categoric theory, you can develop some deep intuitions about abstractions. This was like we scratched like the surface of it, right? You create a very powerful vocabulary to communicate with other people. Like, okay, this program looks like we could use a monad to solve it, or like how we combine the errors. We could have, if we have a semi-group, we could combine the errors, or like we can perform this validation using an applicative to combine like if errors occur. All these are like different abstractions that need time, as it's mentioned, takes time to build. Like you need a lot of time to spend and study about this stuff, but at the end, it comes natural. And the interesting thing is like, you see how these are related to each other and how these get combined. Because, I don't know if you have heard of have you heard about monads? Yes. You've heard, okay, not a lot of people. Okay, there is this famous quote that's somewhat a brain fuck, like some people are saying, what is a monad? Well, they say like, monad is a monoid in the category of endofunctors. It's like, yeah, it's totally brain fuck, but hopefully after today, you know what is a category, what is a monoid, what is a functor, so you could have some idea of what that could be. And essentially this proves that like a monad is a combination in some weird way of like stuff that we already discussed about. Where to go next if you are interested? The first guy, this Bartosz Milewski, is like evangelist of category theory. He's a keynote speaker in all major functional conferences. And actually these three are not just videos, they're like lists of videos. I'm gonna share that, by the way, the slides on Twitter, or I don't know if maybe using the app there is some way. I will share that if you're interested. But yeah, it's like lists of videos. So there are a lot of hours if you would be up for watching category theory. Philip Walder, we're gonna see in a bit, propositions as types. This is actually another way of stating the Carry-Howard correspondence. It's also named propositions as types. Pragmatic Introduction to Category Theory by Daniela Sfregola, which actually was the initial talk that inspired me into giving this talk. And definitely some books, like the Functional Programming in Scala, also known as the Red Book, is like, for me, maybe the best book to start for functional programming in Scala, and also the Cats for purely functional things. And lastly, a talk by my colleague Fabio Labella, Compose Your Program Flow with Stream, that's about composing your program in declarative flows using a specific library, FS2. So, I'm from Ovo Energy, and we are hiring. So if you are up for moving in London and working and doing functional stuff, come and talk to me. There's also a website about careers, but yeah, feel free to come and talk to me. Special mention to this guy, Philip Walder. This is a current professor in the University of Edinburgh, and he was involved in the generics of Java 5, and he was the one that imported monad in Haskell. And to paraphrase a quote of his, remember, when you have a very difficult problem, this is a job for functional programming. Thank you very much. I think we have time for questions, right?
Yeah, we got 5 minutes for questions. Who's first? Put your hand up. Thomas, tell me.
Yes.
You're here to share your experience with us. You're here to talk us through some things like you said is not a well-known principle here with the
yes, functional programming.
with the functional
this
programming.
is how I feel. I don't know.
The other bit I found interesting. You're here to recruit also.
Yes, we're actively recruiting in my company. So yeah, why not? If you're interested, come and talk to me.
Is the industry expanding where you are?
Definitely, and this is like actually this is like one big motivator, right? Functional programming is very hot topic. Like I would argue worldwide, like if you know functional programming, it's very easy to find a job because it's considered the right way to structure code, and like many companies are actively moving towards that direction. So yeah, I would argue definitely give it a shot. And definitely it's expanding, it's very popular, especially in London.
And is it something relatively new? Is it something relative? Because you know we hear about certain areas of development which are sexy, to put it that way. Is this a non-sexy area of coding?
Yes, actually, this is a very interesting thing in the manner that functional programming has been around, I don't know, for a lot of years, I don't know, 30 years or something. But actually now and very recently has been adopted widely, and actually people are starting to write in code and appreciate it. Like there is in a talk of Philip Walder, he's saying, like life is easy, just have an amazing idea and wait for 30 years, and eventually everybody's gonna appreciate it. So it's a bit something like that. So it's been, yeah. And this is actually a good sign, which means that it's been around, it's been tested. So it took some time, like for the industry to actually appreciate it and adopt it, but I think that there's no turning back. So from now on, it's gonna go only up, and the adoption is gonna become more significant in the future.
Okay, so it's something for us to bear in mind. There was another point which, right, okay. There's two more points. Have I monopolized all the question time? Does somebody else want to ask a question? No, it seems like you've only got me, Thomas. I'm sorry, mate.
No, it's great.
Right, okay. There was another question. Now, I watched something recently on the BBC, and it was, yeah, you'll have your turn. And it was that exact question that you asked was mathematics. Was it discovered
Or invented.
or invented?
Yeah, this is
And it was a fascinating Hannah Fry. If you ever get a chance to see it, I mean, watching Hannah Fry on the BBC is a delight anyway. But yeah, it was going through this idea of mathematics. Is it something discovered or invented? Can we have a show of hands here? Who thinks mathematics was discovered? It's something that's always existed, and somebody just went, there it is. Right, okay. And who thinks it is a human invention? Now, that's 50-50, isn't it? That's 50-50 of anybody's money. And you're smart people. You should know the answer. And you're arguing with each other. Thomas, it's been an absolute pleasure having you here.
It was my
Now,
pleasure.
you're going back to London.
Yeah, I'm flying.
Right, and you're going to take a bit of Thessaloniki back with you.
Yeah, oh my God,
it's-
that's so exciting. Yeah, thank you very much.
It's Thessaloniki olive tree. You're going to take it back. You are going to spread the olives and spread the love.
I'll definitely do that. Thanks
All right.
a lot.
Thank you very much, mate. Come on. No. Sorry. No. I'm getting a little bit before myself. Now, give me your name.
Fotis.
Fotis has got a question for you.
Hi, Fatis.
Hello.
Hi.
In the beginning, you talked about compositionality. So, what is the set of mathematical methodologies that segregated maps onto applications in software engineering?
Sorry, what is the? Can you repeat, please?
What is the right segregation? What are the categories of whatever math offers that can have software engineering applications, like formal methods? What other categories were there? Is that the complete set, or
No, actually,
doesn't work this
it
way,
was a bit
maybe?
biased set, so that because that maybe I should go this way.
I mean, there are many things. There's set theory. There's an
Yeah, but this is an interesting thing. The argument, especially with category theory, is like it's so abstract that it covers everything all. Like set theory is like assembly language for the corresponding of assembly language in maths. So category theory is the most abstract thing, and by meaning abstract, it's about compositionality and like how to structure your logic. So this is like the argument that it is the ultimate way to use. But yeah, you can argue like type theory or like lambda calculus that is argued. It's also another branch of mathematics with essentially type theory. Like lambda calculus is argued that it's the first functional language that was ever created. So there is a lot of overlap there. It's not that definite, but yeah, currently what is being considered that like category theory is the way to go.
I guess my question was, with the least amount of elements and with the least amount of overlap, how can you cover everything that you can apply in software engineering? I mean, categories like what you just said about category theory.
The least amount of overlap. Actually,
Or maybe category theory covers.
category theory covers everything, but there is the argument in category theory that you should there are a lot of different abstractions, and the argument is that at any case you should use there's the law, let's say, of using the least powerful abstraction that solves your problem. So like going more powerful means like more laws or like more stuff that.
Invariance.
Sorry.
More invariance, maybe more.
Yeah.
No, that's a formal theory. Anyway, does anyone else have I'm sorry I'm taking this over.
No, it's okay. I don't think we have time. I don't think there's a big issue there. But yeah, I'm not sure, maybe I'm not sure I understand the question, but yeah, I would argue that definitely currently the tendency is that category theory covers everything, is the definitely way to go, and like it's above set theory or like type theory and logic. And actually, yeah, as it is the Curry-Howard correspondence, like these stuff are the same, right?
All right, thanks.
No worries.
Okay, if anyone has any more questions, Thomas, you're on the Hoover app.
Yes, I will be in 5 minutes.
The answer's yes.
Yes,
Right, let's
yes.
try that one again. You're on the Hoover app.
Yes, of course.
Right. Okay. So if you any more interaction with Thomas, take it through the Hoover app, and he'll be able to deliberate your answers because, as he just said, what we need to do with the categories is the point of least resistance.
Yeah, actually.
It's the point of least resistance, and at the moment, the point of least resistance is for me to get a cup of coffee, for you to go out, mingle and network, and make sure, go on the Hoover app and put your opinions, give it a little half heart, and I'll be seeing you in half an hour's time.
Thank you.